Hello and welcome to everyone to episode 7 of Talking Shop with Tony Abbey. My name is David Quinn, Chief Marketing Officer with NAFEMS, and I'll be your host for today. This series is a part of the wider NAFEMS community program of online events that we're delighted to be bringing you. You can see more details on the website and hopefully find something else of interest as well. This week, Tony's looking at topology optimization and generative design. So without wasting any more time, I'll hand you straight over to Tony.
Thank you very much, David, and welcome to session 7, Topology Optimization, Generative Design. So let's get straight into it. Topology optimization is really a subset of a set of optimization techniques which have been around for a very, very long time. So I just thought I'd start off by sort of putting topology optimization in perspective, and then I'll bring the idea of generative design in as well. That was the kind of the teaser, what's it all about kind of thing. So optimization, the earliest approach was sizing optimization, where we just took the physical properties of the element, so typically like a plate thickness, and we could say there are 10 regions, 10 plate thicknesses, and drive those around. So the mesh was fixed, everything was fixed, and the only thing we're playing around with was, again, the physical properties. So it could easily be attacked, as it were, from the optimization point of view. And quite a few solvers, and still have, and still very important and powerful, the ability to drive those sizing optimization. Shape optimization was basically started off by taking a mesh and now distorting that mesh around to get different shapes. Now that was pretty clunky in the early days. We worked hard at it. There was all sorts of techniques in doing that, but keeping basically the mesh topology constant. So again, initially just a constant mesh. So modern methods now have blurred those boundaries. So shape optimization now typically you would remesh as the shape starts to distort to the point where you just can't keep that mesh running with you. So that's kind of had an update. That's got kind of more modernized, become more popular fairly recently with that type of technology. But topology optimization, I can remember when it was like a little toy, and you could show, hey, we can get what's called a Michel structure out, we can get basic structures out, and it was like a checkerboard type of approach. Basically, the idea is that you're eroding elements from a fixed mesh, so the mesh topology and shape is actually constant, but it's the elements that form the new shape and form the new topology. I'm already starting to blur the distinctions between shape and topology. Strictly speaking, a shape is a constant topology, and you're morphing that shape around. Topology, you're popping new holes in, new voids, changing the boundary, and so on. So basically, topology is like the wild child. You can do anything you like with that resulting topology or shape, but it's usually laid on a fixed mesh. So that's the background to what's been going on. So for many years, I started doing sizing optimization about 75, 76. In fact, I just did my MSc thesis on sizing optimization. So yeah, there you go. That was in the mid-70s. So it's been around a long time, but some things happened to kind of change all that. So we're actually going through a renaissance of structural analysis, and it's basically because of the influence of the ability to do topology optimization, generative design, and actually build something with it. So the resultant structures coming out, we can actually now make them. So additive manufacturing and prototype manufacturing, and then additive manufacturing has meant these weird-looking designs, we can actually do something with them. I can remember probably about my second year in the aircraft industry coming out with the sizing optimization, and I just basically said to let every size of every wing panel do whatever it wants to do to get some sort of feel for what's going on. I can remember taking that and showing that to my chief stressman and chief designer as an idea, and they just go away, laddie. That's just too crazy. We can't make this. We just want to have 3 or 4 variations of wing thickness and so on. Same with a bracket. I can remember coming up with a non-symmetric bracket or lug, and it's like, no, take it away. We always do symmetric designs and so on. So it's basically it's an exciting new breakthrough because the traditional methods, sizing and shape, in many ways they're kind of boring, and I found that they kind of reached like a plateau of usage. People use them. People are very experienced using them. They're very, very effective, but they were kind of a small, I guess, relatively niche area, and it was the same old kind of processes being gone through. So topology optimization was there, but as I say, it was a bit of a toy. The fundamental approach has been known for a long time, but again, now we can actually do something with it. So this breakthrough this kind of exciting new introduction into optimization, I call it the optimization renaissance, is essentially rapid prototyping, now becoming now obviously additive manufacturing. So we have many more mainstream possibilities now. And if you look at, I think that you can look at Google hits or Google searches or a number of papers produced on different things. And I think there's been an explosion of interest in optimization. And it's all based around heavily topology optimization. I just had a note popped up from Marcel Edelkamp. Do I remember when we were working on Shape and Topo coming out of Karlsruhe University back in the late 90s? Yes, I do. And that was the beginning of the Renaissance. So thank you, Marcel. That's a great prompt. To my mind, that Renaissance started to happen around about 2000. It started to get mainstream with particularly the shape was transforming. But when we come to topology optimization, it's really now we can actually build things at the back end. So we've got a maturation of the topology optimization techniques. There's some very cool new techniques have come in the last 4 or 5 years. There's even more coming along. So it's not a stable technology in the sense of it's not a done deal. So I'll try and sort of illustrate as I go through some of the new areas that are coming through, things which make it very, very interesting. So the technologies are getting more stable, they're industrial strength. I can remember playing around 10, 15 years ago with, again, toy type of approaches, if you like. They were like demonstrators and they were very, very interesting, but we couldn't really build structures or go through a kind of complete design workflow with them. There are many new topology optimization-based products appearing in the marketplace now. It's, again, this big explosion of usage. There's lots of people jumping on, if you like, onto the bandwagon, but obviously a lot of hard work to develop this kind of technology and get it out there. The focus now is more, I think, on the manufacturing process. We need to extend this simulation to include manufacturing, particularly if it's additive manufacturing. But also, not to be overlooked, we can actually use subtractive manufacturing, traditional machining, milling, those type of techniques. With the controls we have now available in the topology optimization tools, it's just as applicable in many ways to more traditional type of machining as opposed to these very radical kind of new designs coming out. And it's really up to you how you control these tools, where you want to go. If you want to have just completely new designs, new white sheet, empty design space, anything goes kind of thing, then you can take that approach. Or you can actually constrain the topology optimizer to say, give me something which is like that has symmetry, has manufacturing constraints, something which I can actually make, but still exploring interesting kind of design candidates. So this is essentially the kind of explosion we're seeing, and now a sort of like a control on that to say now we've got to be able to come up with some things which are more practical. So you can be very radical, new organic new designs, or you can be kind of more conservative as well. Now we've also got terms such as generative design are appearing as a warm-up or some research for this little talk. I went through and looked at the definitions of generative design from about 5 or 6 software vendors, and they're all over the map. And I thought there isn't really, it's like a lot of things. There's probably in the dictionary there's a definition of generative design, but essentially it comes down to what does it mean to you. There's some really I've got to say some very bad presentations on topology. Well, generative design can do anything. Everybody should be doing generative design. You kind of, if you're not there, you're not cool kind of thing. In fact, generative design, I'm seeing some parametric design operations where you're actually perturbing existing dimensions rather than going for topology optimization. And I think that will fit in at some point as well. I don't think it's quite there yet, but it will as well. So some of the formal definitions of topology optimization are beginning to blur. One of these presentations, it was described as shape optimization. People talking about shapes. But I guess perhaps I'm being a little bit kind of pedantic there, but topology optimization is all about changing topologies. Shape is about morphing existing shapes around. But again, the definitions are blurring. But what kind of worries me a little bit is with this big explosion, have we lost track of what is it we're actually trying to do, what do the tools offer, and what are the design drivers, and what can we actually achieve with topology optimization? The danger is it becomes like a push-button operation. Who has the slickest set of buttons, if you like, to push, and out comes all of this, these solutions, and the machine, if you like, picks the best solution for us. That's obviously dangerous. We've got a lot of design capability, a lot of design skills, and so on. What we want to do is harness those design skills with the technologies which are emerging, not obviously not just replace them. So just a little bit tongue-in-cheek, earliest optimization was probably based on observation and experiment. So there's an old story about, here's the square wheels, the corners get knocked off, and then the performance improved. And hey, it's a form of kind of like literal topology optimization, if you like. We're whittling away material, and we're improving the performance. Flying buttresses are my favorite. Way back, 12th century optimization. How did these guys come up with these very elaborate shapes? This is a kind of the cathedral here, and we go to these very heavy roofs, and we've got to spread that load out. The walls can't take it. They've got side loads, thrust loads, so we're spreading load out into the massive masonry stack here through very, very elegant structures. Something that would be topology optimizer would be very proud of to actually be able to achieve that. So again, it's this idea of exploring new shapes, new candidates, new designs has been around for a long time. But now we have perhaps an automated way of doing it. I like to look at bridges, for example. In England, Brunel, Victorian engineers, Victorian means from, what is it, about 1860 to about 1900, that era, Industrial Revolution. Here are 3 bridges, and they're fundamentally doing the same thing. We've got to get from one side to another. We've got to traverse across a bridge or a river, whatever it is. We're carrying load across here. But look at this, 3 completely radical designs. And you could say, well, what was going on? What was the thought process going on in there? So these are basically candidate designs. And the key to optimization is evaluating the strengths and weaknesses of these candidate designs, coming up with them, and then saying, do we like them? Do we not like them? What are the advantages? And so on. So in a nutshell, I think that's what topology optimization, if you like, is the engine. And then we could describe generative design as the process to say, how can we choose these? Which ones do we select as the best candidates, and which one do we then finally run with? And then sort of, I guess, how do we build it at the end of the day? So this is the idea. We're looking at a range of different sort of candidate structures or generated kind of designs. So topology optimization, again, just to be very clear, it's basically, it removes the limitation of shape optimization. Shape optimization would be this thing here with one boundary and 2 holes, and you can push and pull that around. You can kind of morph it. Topology optimization says you can do what you like with it. There's only one outer boundary, but as many inner boundaries of voids as you want in there. So that's basically the new approach which is being brought in there. How do we map that into structural analysis? Well, we typically, the approach taken is to have a fixed mesh, and so we've got a domain of elements. And what we're doing is we are not changing the geometry. We're actually are not morphing the mesh. The mesh stays constant, and we're just removing elements from that mesh. So we're just knocking out, deleting elements. So we vary our boundary and introduce voids by deleting the elements. So there's a little example here. We've got half symmetry in here. There's a distributed load across here. There's a supporter there. And lo and behold, we got a half symmetric bridge type of solution coming out, as it were, automatically. Now, there's a couple of issues with this. Because we are using a mesh-based approach, the high fidelity of CAD to FE mesh isn't maintained, and that's a problem for us. So, how do we interpret this picture up over here on the bottom right and turn that into some sort of geometry? Well, that really is probably another talk, and that's a very, very kind of big topic. But basically, we can't come up with most topology optimizers at the moment can't come up with distinct boundaries. We get an indication of what the boundary should look like. So this is an indication of what the boundary should look like and what the geometry fit should be through there. So topology optimization, we're getting rid of elements from our design space. We've got hard kill methods which actually delete the elements from the model, or they have a binary state where you say you've got basically chewing gum or the full material. And I've said the density and the Young's modulus goes with it. So that's used in the earlier evolutionary methods. So the evolutionary methods and the bidirectional evolutionary methods. So Bezo methods are still around. And also the level set methods. Again, I could do another talk on these different technologies, but level set is a new technology coming in, which has an interesting kind of approach to it. So hard kill method, we're actually going to knock elements out. Soft kill method, it's inefficient and just a difficult process to do that. So this SIMP method was the basis here. We're going to say we can have a variation of material density and, well, if we use density as the design variable, from chewing gum, very, very soft chewing gum, very, very low density, and Young's modulus, to our parent material. So we have this, this transition of material. So the boundaries and voids are now created by solid, full of density, and then empty, but then transition of material in there. Now the problem is that we've got transitional material, it doesn't represent anything, so we use a power law, which is where the P comes in this process, to say cluster towards material which has been very low density, a low material stiffness, and very high density, which is getting close to our parent material. So just basically pushing these boundaries around a little bit. So again, I've got, if anybody's interested, we just finished up actually yesterday the optimization e-learning class, and so I go into a lot more detail of what goes on in there. Now, what are we trying to do with the topology optimization goals? Notice I'm talking about topology optimization. I explain why in a few slides. The actual objective function, what we're trying to do with an optimizer, that's what we're trying to minimize or maximize traditionally. They can include maximizing homogeneousness, which is a very interesting approach. We're actually smoothing stress gradients. So getting the smoothest possible stress gradients subject to a target mass. That was used more in the shape methods that Marcel kind of reminded me of. And that was interesting. That actually goes back all the way to what we call an optimality criteria, where it sounds like a good idea. If we smooth stresses, that's going to give us efficient structures. We can also minimize compliance. We can think of that as optimality criteria. Seems like a good idea. But people have actually worked very hard to show that minimizing compliance, you can show that mathematically that will actually show an optimum solution. So some of these are kind of like a little bit woolly. It seems like a good idea, like fully stressed design, for example, homogeneousness. Some are actually a hard mathematical definition. We can also minimize mass subject to target stress, and other strategies are evolving. The most common one, though, is going to be minimizing compliance, which means maximizing stiffness subject to a target mass. So that's our typical volume fraction, say 0.7. Let's get rid of 30% of the mass, and let's make that as basically as maximizing stiffness, minimizing compliance are very similar kind of statements. So we're coming up with very, very efficient structures, and the constraint is actually on the mass. Now we've actually starting to see evolving now new strategies. So like, for example, minimizing mass directly to a target stress, for example. And so that's things are changing from the basic kind of, this is the minimizing compliance subject to a volume fraction is kind of the starting point. So what we're trying to do is to derive a level of efficiency is the objective, with some kind of target constraint to drive it, is the fundamental approach which is taken with all of these topology optimizers. What are the constraints? So we've got the objective is to minimize or maximize something. What are the constraints on there? Well, as I mentioned before, traditionally volume fraction, we had for target reduction in volume fraction, which we essentially have to guess. Let's get down to 20% material, 30% material, 40% material, whilst minimizing compliance, making that solution when we get there as efficient as possible. And that's the basis of most generative design methods or topology optimization methods. But there are new methods evolving which include we actually driving, say, minimizing compliance, but to a global stress constraint or a global displacement constraint or a frequency constraint. That means that we're actually getting more viable structures directly. With the traditional approach, which we'll be looking at, you get what you get in terms of stresses or deflections. To some extent, obviously if you're maximizing stiffness, you're driving down displacement. But if you want to make it a specific displacement target, then these new methods coming in are developing. The mathematics behind them, the technology behind them is fiendishly difficult. It's a very difficult technology, so people are gradually moving forward in this area. But what I like about this is we're getting to the stage where maybe the generative design, where we just have a huge scatter of potential designs, half of them are not going to be strong enough, half of them are not going to be stiff enough. Maybe we can get that up front. So this big scatter of generative designs, where we're exploring all of these candidate structures, we can eliminate. We don't have to waste our time looking at things which are just not viable to us. That is becoming like a tighter bound on the type of solutions that we can look at. Some solvers have those technologies, some don't. So the approach is going to vary, really very much dependent on what your tool set is there. So I've got a couple of examples, and I got to thank a couple of software vendors. I do a series of articles for Digital Engineering magazine. I get loaned these licenses, and what I like to go there through is that just when I'm driving the software, not just kind of go through the benchmarks or what I like to get my hands on, actually drive and actually try out these things. So thank you to Altair, Solid Thinking, Inspire for this. This is a bracket with two load cases. We've got a design space in here, which is the vertical region. The fixed space is not a design space. Notice we've got a fixed width here. I've chosen design space, and I've actually locked in already a condition which, to resist that horizontal load, I'd really like that width to be as big as possible. So when we're choosing design space, we've got to be a little bit sensible about how we do that. That's just a little tiptoe into some of the practicalities of you can't just set up these problems, press the button, and away you go. There's a whole load of other stuff to be talking about and thinking about. And again, maybe another talk we can get to that. But again, the objective is to minimize the compliance, maximize the stiffness. The constraint is a target volume fraction. So that's basically what we're doing. Now here's the first trial. I just said let's get to 30% volume, so we whittled away. We got down to this material. And it's the SIMP method, which means this gradation of density from like chewing gum, hopefully somewhere in here, solid material in the depth in here, but a transitional material in a boundary region in here, which is why this particular software gives you a little slider bar to say, well, you can actually play around with that. Where's the definition of the boundary material in here? Well, it's a little bit subjective. Now, what Solid Thinking does is then you can actually fit NURB surfaces through here, so you can kind of clean up that surface and then move forward. That's very important. Many other software does a similar kind of task. But you can see that it's a little bit subjective. What does that 30% volume mean? Well, it's kind of like, again, we are knocking out elements. We've got to smooth our stress distribution through here, smooth the density distribution through here, and I sometimes call it like a one-eyed squint at the stress distribution. Gives us some feel for what the actual final structure should look like. So there's some cleanup, some fitting required to actually achieve that. So this is topology optimization, and it's like a one-shot topology solution, optimization solution. But what good does this one-shot do us? Not very much on its own. And so my definition really is that topology optimization is the foundation for generative design. One configuration isn't enough. We need to look at a lot more. And I think that's really what, to my mind, that's what generative design is, to say one instance of a topology optimization isn't good enough. We need to look at lots of them. Now, sometimes I see people saying, well, hey, we've got generative design. It's not just topology optimization. That's not good enough. Well, I don't know anybody that would do just one run of this and say, I know that 30% volume is right. We know that we've got to iterate. We've got to kind of play around and so on. And that's really the essence of what we're trying to do. So if we take that idea, here are my design candidates. What I've done here is to say this is the mass achieved by each dot in here as a target volume fraction. So I don't know where 30% is. It's somewhere down in here. Actually, it will be, well, I don't know quite where it is. But basically, this is my mass, and that's actually a mass in kilograms, I think, not a volume fraction. And this is the compliance. So basically, the lower the compliance, the stiffer the structure. So that's basically the idea. Now, if I maximize stiffness, minimize compliance, I get the blue curve. And what I'm interested in now is the variation. Up here, I've got chunky structures which are over-designed. down in here, I've got structures which are basically the dashed line there fails. It's a structure which can't hang together, and in fact, the optimizer can't get continuous material across there because it just run out of enough material there. So somewhere in here is going to be my design which is strong enough, stiff enough, and very efficient. Now this curve, which you're looking at, the mass and compliance, these are both, we can think of these as being both objectives now, and it's what's called like a Pareto curve. So it's basically saying, just look at the blue line, because what the topology optimization has done at each instant is given us the most efficient structure. So we're only looking at the most efficient structures here. We can discard anything else in there. So it's, again, we've got a lot of candidates, but there's some meaning behind them. So I'm always a little bit concerned about generative designs which are producing thousands of designs. How do we actually come up with a strategy to say these are the ones we want? Well, this Pareto curve, I'm going to make a decision. Do I want it to be heavy and stiff, or very light and very flexible? That's my decision as a designer. I can make my choice along here. Interesting, I also put in minimize the mass and at the same time work on the volume fraction at the same time minimize the compliance. So in that particular case, I get a different curve in there, and they kind of interact at that particular point in there. So that's interesting. Coming at it from two different perspectives, I seem to end up with about that kind of mass. So the interpretation of the best design is very subjective. And really what we're trying to do, I think, in generative design, like in most optimization, is to avoid that definition of the best. And I think that's why people now talk about lightweighting rather than optimization. I can remember optimization has a bit of a stigma. I can remember when we were in the early 70s, people would come up with benchmarks like the 3-bar truss and so on. Somebody would say, well, I got a better optimizer because I got 6 significant figures. I get a lighter structure than yours. Well, those days are over, really. We're thinking about the practicality, the broad brush applications of somewhere in here is the most efficient design we're interested in. Give me these configurations. Give me these candidates. That's what we want to be getting from topology optimization as the engine. Generative design, in whatever form it takes, is basically the delivery mechanism saying, hey, here are the choices that you get. So here, topology optimization is giving me a series of trade-off studies. Again, thanks to Paramatters, CogniCAD, and thank you very much, Michael, for support here. This is a different problem I set up. It's got a design space. We've got some supports in here, which we mustn't be whittling away, some supports in here. And there's a container space, something that's going to fit in here, so we mustn't go into that space. Here, there's 400G lateral, 400G vertical, and it's the same idea. I can come up with a one-shot design, but that doesn't do me much good. So what I've done here is to actually look at, again, traditional type of approach. I'm basically saying minimize compliance subject to a target volume fraction. So each of these designs is a different target volume fraction, and it's a traditional trade-off. What's interesting here, it's just one optimization, and it's dealing with the two load cases at the same time, but actually is reporting the compliance of those two load cases. So it's interesting there, you can actually see which load case is dominating. In each case of those, it's the lateral load case, which you probably expect, the torsional resistance, which is dominating there. We can also see that there's like down in here up to about, say, 0.1 kilograms, it's fairly straightforward, and then it starts to get very spindly, very flexible, as shown by the very high compliance. That's giving us very useful information. Do we want to go to the more robust structures, or do we want to go to our kind of spindlier type of structures? So you can see this is a form of generative design, because we're not just saying, let's run that one, say, and give us whatever that volume fraction is and see what's happening. That's really not much good to us. We want to look at these trade-off studies. So really, topology optimization, again, that's the one-shot solution. The multiple topology optimizations, whatever you want to call it, they're calling it generative designs. In many cases, I just call it like an optimization strategy. Whatever you want to call it, it's basically exploring what our options are. Looking at trade-offs, not just looking at the single optimum. That, again, is a very kind of sterile thing to be doing. Now, this optimizer actually fits through smooth geometric surfaces through the configuration that evolves. So the stresses are actually a very good approximation to those which will be present in the resultant geometry. Again, the two curves are basically the two load cases. So you can see that that lateral load case, the torsion, is dominating. And again, the stresses are doing okay, until we get to this point in here, and so the stresses are too high. And we see the similar trend for displacement, and this is very useful. We can see that, okay, these are viable. Now we rapidly go into non-viable kind of areas. So armed with a little bit more information, kind of digging in a little bit more, we can actually see what's going on. So again, this is the kind of tools we need to be able to sort of rank and sort and decide which of these particular configurations we like. What we can do now is this, because we've got smooth surfaces, this particular software can actually apply stress as a constraint rather than applying volume fraction. So the objective is still to minimize compliance, but I'm working directly against the stress constraint. And this is what I was alluding to before. If we can do this, and later developments, hopefully we're going to be looking at displacement constraints as well, we're immediately narrowing that field to stuff we have to junk because it's going to be too flexible, stress is too high. Within the topology optimizer search, we're actually going to be able to eliminate that and keep within the domain of things which are useful. So the black line here is actually showing a run where we've got the stress constraint. One we set at 300 megapascals, one set at 400 megapascals. So what's happening is we actually get a lighter design which is satisfying the stress requirements. These violate the stress requirements. So we've got lightness here, but we've met our stress requirements. Unfortunately, the deflections are much higher, as we'd expect, so we'd have to look carefully at the deflections. At the moment, we can't simultaneously apply deflection constraints and stress constraints, but when we can start to do that, then we can get to more viable designs more quickly. I still wouldn't want to come up to the optimum. I'd still want to look at a range of candidates and still have a lot of flexibility so that, again, think of those three bridges. I want to look at interesting candidate solutions. I don't want to get driven down to kind of like a narrow definition. And that's really the trick with topology optimization and generative designs, not get kind of forced down into a narrow dead end, which is kind of not limiting perhaps some more radical solutions. There's all sorts of things that we're looking forward to the future. When topology optimization meets evolutionary genetic algorithms, for example, genetic algorithms can do all sorts of things there. So a very interesting comparison of the solutions here and all the other solutions. We could perhaps later on we could look at displacement constraint solution, and we can start to make decisions on which way we want to go here. So my take on generative design is it for sure builds on the shoulders of topology optimization, but maybe later on we can also be looking at parametric design optimization, so essentially shape optimization, where we can drive CAD around in a more sensible, more rational way. At the moment it's mainly based on topology optimization, but we need a strategy up front to avoid a huge volume of worthless candidate structures. If we get a huge bin of 1,000 candidate structures, now we've got to wade through these in some way. Why are we starting with all this? Why are we wasting our time with things which are worthless? So that we need a strategy in there. And that could be a strategy in the software. It's just a strategy you evolve to say, this is, posing the optimization problem is the way we always put it. If you pose the optimization problem well, you're going to get a good answer out. In other words, if you ask the questions, the right questions, pose the questions well, you're probably going to get a good solution coming out. So we also need a selection process to identify the promising candidates. When I see great tables of design solutions coming out, well, how do I start to sort and figure out what is the most promising? I don't want to go for some true optimum, the optimum, but I want to be able to say this is a promising kind of region. I also believe in reverse engineering. When we get the best structures coming out, I really like to look at these and say, well, okay, I've been given some guidance here. Now as an engineer, what do I make of these load paths? Why have we got material in these particular, distributed in these particular ways? So I'm not just going to take it, I'm just going to say, can I learn something from it? And I think reverse engineering and understanding what's happening actually helps your knowledge of structures, load paths. It's giving you, if you like, experience coming directly from the machine solution, but then you can kind of say, well, what does this mean to me? So you can learn from that. It's not just a push button process popping out these marvelous solutions, which we say, well, that's great. It's a machine design. It's got to be good. The engineer really needs to be in the loop here, and this This is what I'm really saying there. So again, thanks very much for watching. That was a very rapid counter through what's a very big topic. Again, the shameless plug here, if you're interested in the background to topology optimization and others a lot more, then please feel free to latch on to the next topology optimization, sorry, the next optimization course I'm running. Now the next section is June the 12th, and this will be news to David. I'm sorry, David. This is going to be about normal modes analysis. It's an essential foundation to any dynamic response analysis. That's a really, if you thought I kind of preaching a little bit about topology optimization, wait till you get to this one. Normal modes is essential for that, so that'll be coming up pretty shortly. So with that, I will finish now and pass over to the sane voice of David Quinn.
That's the first time in quite a while I've been called sane, Tony. Thank you very much. I hope everyone's enjoyed today's presentation from Tony there. We do have a good number of questions on the Q&A.
Steve Fisher says, we were using topology back 2000 to investigate when we needed to improve a design. Kind of welcome back. Absolutely, Steve. Topology optimization has been around for a long time. It's just now kind of hit mainstream. Ivor, hi again, Ivor. Today, topology optimum is still based on running through a series of loads we decide to define, but one always forgets some load cases, and the parts break easily in true tests. So testing is even more important. Clearly, a very interesting new method. Yes, I emphasize I'm just dipping into this big subject. One of the things I always say is that if you forget to define a load case in topology optimization or any form of optimization, you pretty well just design a structure which is guaranteed to break. And what you're extending that to, Ivor, is to say we also need tests to make sure that our, the way we describe the loading in the analysis side, the virtual loading, again, is that adequate to define the real world. But at its simplest level, if we leave off a load case, then we're in serious trouble. So getting at robust solutions is very important. So good point, Ivor. Steve Fisher again says, to use optimization correctly, you need to be a very good engineer. I like the emphasis on the very good engineer. You need to understand why the optimizer is giving you that design. Unfortunately, some people will use optimization without actually understanding this issue. That's really the point I was trying to make there. I completely agree. I don't want it just to be a machine process. You take that very interesting result, you go and use it directly. So I'm trying to say in my summary, it's like, why are we doing it? How are we doing it? And then what's it telling us? What can we learn from that? James says, for the soft kill methods, what is your opinion on using stress as a target constraint due to the load path going partially through the low density regions? Is there a good way to approach this? Yes, what you've got to do is to kind of smooth that stress distribution. So normally in static stress analysis, we're saying don't ever take average stress results, look for the maximum stress result. Here we're doing the opposite way around. It's what I describe as this one-eyed squint. We're basically saying what's the configuration likely to be underneath here, so smoothing stresses, taking average stresses. We know that boundary in the soft kill methods is a very approximate boundary. Where is it in space? We don't know. So basically, it's basically coming up with that surface or the shapes, the edge, the domain of the finite element mesh is useless to us because by definition we're going to have stress concentrations all over the place. We're kind of smoothing through that. What you can do is to check designs, you can take the geometry which has been implied. So again, there are many techniques. We saw, for example, Solid Thinking has one approach. CogniCAD has another approach to basically backfitting geometry through these regions, these transition regions, and then either approximating the stresses through there or getting more accurate representations of stresses. So you've got to take that transition from what you're given with like that fixed kind of clunky mesh to your interpretation and reinterpretation, maybe through geometry, maybe through remeshing to get to a better stress representation. There are lots of different approaches we can take there. The ultimate would be to fit your new geometry through and then rerun it to see what stresses come out. But you want to be able to do that more intimately, more interactively, and that's one of the big pushes, which is going on at the moment in topology optimization. Ivor makes a comment: in nature, the shape optimization smooths the surfaces via similarity to surface tension. I haven't really seen this implemented in the softwares today. I think that's where the stress making homogeneous or smooth stress distribution is the closest. That's like an optimality criteria approach. Seems to be like a very good approach, and it seems to work pretty well for shape optimization. The idea is if you smooth stress distribution, you're going to have an optimum structure where the stresses tend to go down. So I think that's perhaps analogous to the surface tension type approach you're talking about there. Darren is asking a question: does St. Venant principle help in optimizing the structure figuratively, since we know how the stress diffuses? That's interesting. Yes, we've got to, if we come up with a topology optimization which is perhaps leading us astray in the sense that a local feature perhaps around a support point or a loading point tends to have a high stress, but everywhere else the stress distribution looks pretty good, then we can use that as an indication that our candidate design is looking very promising overall, but we need to pay more attention to the support points or to the loading points. So there, yes, I often use St. Venant principle in the sense that if I can see a high stress region and I can't get rid of it, I might turn that into a region of the design space which is not going to be changed, and just accept that high stress which is sitting there, knowing that I can come back and I do something more subtle with that local detail. So yes, that kind of plays a role. And that really comes down to, I think, Steve's point, which is basically we want to use engineering judgment here. We don't want to be, if you can imagine, get one hotspot stress for some reason and it's a poor modeling, or we haven't set up the problem very well, we're going to be driven by that hotspot stress in the optimization globally. Well, let's get rid of it. Let's sidestep it somehow and then move forward. So that's basically the approach side wrap up in there. Badri asked the question: how does topology optimization related to evolutionary structural optimization? Is the one-hand calculation the evolutionary structural optimization a version of the topology optimization? Yeah, you basically got evolutionary methods which tend to just directly work on, in my course, we work on fully stressed design, we work on stress, then we show that that's not a good thing to work on, so we actually look at sensitivity. So basically, if we remove material, does the compliance change? If the compliance doesn't change, then that's a great candidate to remove material. That we could call a direct evolutionary type of approach. Then there are the SIMP methods and the level set methods. There might be other methods out there, but those are three classifications I've come across. So they are all different approaches to topology optimization. I describe topology optimization as kind of the engine behind generative design, but there are different ways of doing topology optimization. Badri also asks, how do we do topology optimization with multiple structures, bolts, and so on? That then gets interesting. It's a very, very big question. Sometimes, if we try and take a wing, for example, and I said, let's do a topology optimization for a wing, and the whole thing is going to be driven from the word go with topology optimization, that's almost doomed to failure because we have our standard fittings, parts, other things we want to do. So there's more like a cascading type approach. We might get initial optimization approach using other methods to get the overall wing layout and so on. Maybe sizing optimization as the final approach is my experience. But what's interesting there, the individual ribs, you might say, well, I can bound the load path through these ribs, so I could use topology optimization to design the ribs. So do I come up with like a plate type rib, or do I come up with like a Warren girder type rib? That distinction and that local detail could be done with, say, topology optimization. There is a danger there because you can show quite easily that optimizing parts and then bringing those optimized parts together isn't necessarily an overall optimum solution. But I think at the moment we just can't handle really complex assemblies and so on. There's just too much engineering kind of going into it. So I think topology optimization, I think maybe overall configurations to get some feel for what's going on, and then actual, if you like, components. But to do the whole thing with topology optimization, I think would be a struggle at the moment. If anybody has any better information, better ideas, please feel free to. I'm going to be posting the videos as usual on LinkedIn and on our website. So delighted to get into more discussion on that. James asked a question: as a cheap optimization tool, could you just use strain energy to understand load paths? Yes, you could use strain energy. Would be a great way of doing it. Strain energy density to understand what's happening. And then what you can do is you can actually start to say, well, let's remove material here, and that will give you perhaps an idea what's happening. But as soon as you remove that material, then you change the load path, so you've actually got to do a little iteration in there. And on the course, I show a fully stressed design approach where I do exactly that. A cheap optimization tool, all I've got is a macro which just basically goes through and says, well, you have stress below a certain level, remove that material, and then at that stress removal level, just iterate till you get a stable load path. That's your first step, and then just keep doing that as you basically remove higher and higher stress levels. Stress isn't a good thing to use, because if we've got indeterminate structures, we get into trouble with that. Strain energy or compliance would be a better thing to use there. So yes, if you can set yourself up a macro to drive down there to remove material, then that's a good way to do it. You're essentially doing then an evolutionary type of approach. Now you have to do a bidirectional, so what you say is, whoops, I'm going down that path, I'm locked into that path. As the load path is changing, maybe this configuration would give me a better load path. So that's when the bidirectional, the BZO method comes in to say, let's back out of that. So as a simple kind of approach to explore what's going on, I think it's a great method. And if you can set yourself up a little macro to go through a couple of iterations, then I think it could be very, very useful. That's how I like on the course to introduce optimization, topology optimization, because we can understand removing inefficient structure by an evolutionary type approach. Badger says example 2 looks like optimization structure of a dinosaur. Yeah. Again, this is where what do you want? Do you want something which looks very similar to what you've always produced before, there's a variation on it, or do you want something very radical? And that's where the optimization tools really at the back end, when you say I want to do symmetry, all sorts of manufacturing constraints such as something that should be extrudable and things like that, you get back to more kind of realizable, well, it's, I guess, the difference between additive manufacturing, which is like the dinosaur type structure, anything goes, but even there you've got to be careful, and there's some more technology to make sure we can build that thing and it doesn't get too weak, too flexible as we're building the additive manufacturing process. It's not as straightforward as it might seem, to something which is catering very much more towards the subtractive manufacturing technology. So how radical do you want to be, and how conventional do you want to be? For example, a lot of very successful shape optimization is done just to improve stress concentrations locally around features to improve fatigue life. So we're not coming up with any kind of radical solutions, we're just perturbing things a little bit. And again, it's very difficult to figure out how to do that kind of intuitively. So let the shape optimizer in that particular case move that surface around until we've got a much better fatigue life. Andrew says, asks, what's my thinking about stochastic topology optimization as overarching strategy where design candidates are evaluated and considered during the optimization run itself? So what we're saying there is that basically we don't know an actual gauge, an actual, well, let's say we don't know Young's modulus exactly, we don't know the loads exactly, so we're going to look at a variation. I've not really seen that meet topology optimization, but it's a very, very important aspect of a real-life optimization. I've tended to work mainly with deterministic type approach, so we've got a particular material property, we've got a load, but I think I bring that in, particularly with my view, is that loading is perhaps our most unknown, and perhaps the supports as well. Supports and unload and loading, that's the biggest variation, I think, that we've come across in the real world. So I like to, I guess, in a poor man's kind of way, make sure I've got lots of load cases. I cover the load cases. Sometimes I would impose symmetry because that way I've got a bidirectional load immediately. I can carry stuff which is loaded from the left, stuff which is loaded from the right. I've not missed off my non-symmetric kind of load cases. So yes, I don't think the disciplines have met yet fully within topology optimization, but I think they're very, very important disciplines in there. James asked the question, have you experience of implementing generative design using additive manufacturing, and how did you find the reliability of additive manufacturing material properties versus those used in the analysis? I haven't directly produced anything that's been made. I've kind of shadowed through. There's a GrabCAD magazine and GE definition. They had a competition of a secondary structure bracket on a jet engine, and that was very interesting to see what had gone on there. I see what you're saying there. Reliability of additive manufacturing material properties. Yeah, again, that's really that downstream question now. We've got the idea right. Now we want to get into the nitty-gritty of can we actually make it. So now we're starting to see modeling of that additive manufacturing process. The classical thing is we produce like shallow arch type structures. They can't support themselves during the build of the additive manufacturing because we're applying pressure, applying temperature. So now that linking of the actual modeling of the additive manufacturing process, linking back to the optimum we're producing, I think perhaps that's where we're going with this question, James. I haven't directly had experience of that, but I'm reading and following with great interest that, because that makes it real. And it may well change the optimum structures and so on. It's a very, very interesting area. Karma is asking the question, is generative design primarily done in CAD? Are there some that are FEA based? No. In fact, generative design is done primarily in FEA. Design Space is using elements. We're knocking elements out. Our challenge then is to transition that Lego brick type definition of the structure with elements missing all over the place into smooth geometry. And the two programs I used here have two different approaches to doing that. So that downstream link back to something we can manufacture, back to real smooth stresses and so on, is very, very important. Generative design done in CAD is very interesting. I did an article on using QuareTime. QuareTime takes the design definition, say in SolidWorks. We've got all of our dimensions, and it uses those dimensions. So it's really a parametric shape optimizer. And I think that is also a tremendous future direction. So there you would be right. We're starting from CAD, perturbing in CAD, and then coming up with solutions. I haven't seen that yet embodied, but fully in terms of like a topology optimization. I think, and it's not really a topology optimization, it's more of a shape optimization. I think that's a very an overlooked area, and I want to see that coming through more strongly. So I like what the guys in QuareTime are doing. There might be other people working in that area. I must stress I try to remain neutral, but the guys there were very helpful, and to drive and perturb parametric designs around, there's a tremendous amount going for that. It's not going to be a radical design necessarily, but you already put a lot of design thought and effort into that, so let's just perturb that around a little bit. James asks, what software am I using? I use a whole variety of software. Using sizing optimization, it's the Nastrans, Altair, OptiStruct, a whole range of different software, ANSYS as well. For the topology optimization, I used the two examples. One used Parametra's CogniCAD, the other one used Solid Thinking Inspire. I've used many other optimizers, which I didn't get a chance to include in here. So many other topology optimizers I played around with. I would emphasize I don't kind of endorse any one of those in particular. It's like a moving target. What I recommend is you get playing around with them, particularly the cloud-based ones. can get a kind of a relatively cheap look at what's going on. So play around. Really, it's an open field at the moment. Nothing's settled down to the best in class yet. I think there's all sorts of very interesting solutions being developed as we talk about. Yeah, John says he liked your comment about using optimization to determine load paths. I hadn't considered that before. I really believe in trying to understand stresses, as I mentioned previously, looking at free body diagrams, is extraordinarily difficult. Optimization can help you actually determine and perhaps emphasize these load paths and understand what the structure is trying to do. You've got load going in, load coming out, and what the optimizer is trying to do is the most efficient distribution of material to achieve that, subject to the objectives we've talked about. So it can be very, very useful to kind of understand what structures are trying to do. Nick says, it appears that topology optimization solutions are great for static designs. Have you found that the optimum top-op solutions are not desirable, topology optimization solutions are not desirable for fatigue purposes? If so, what's a good workaround? This is where there's a lot of work going on. Static design, as evidenced by minimizing compliance, has been typically the starting point, and now we're starting to see dynamic analysis coming in, and now quite a few solvers can handle normal modes analysis, for example. I've seen some extensions into fatigue analysis. I haven't really followed them through yet, so I would expect over the next 5-10 years more disciplines are going to be embraced in there. Nonlinear would be a challenge, and so nonlinear analysis would I see the evidence of that coming through. As I said, dynamics is coming through very strongly. I've seen evidence of fatigue. The workaround would be, I guess, for fatigue to say let's minimize the stress, the peak stresses. But again, at the moment, it tends to be a global peak stress. You perhaps want to get a more of a local peak stress. So that would be a good workaround at the moment. David asks the question, would you agree an important control parameter is the accepted slenderness of these structures? Maybe something like how do we choose between a spider's web versus a starfish? Yeah, so we have like a minimum member dimension. That is one of the control parameters that we can put in. So I describe it as like, you can end up with like a filigree type structure, or you can end up with a more chunky type of structure. And then again, that's something which is, that's where the design intent, the engineering judgment call comes in. Can we accept something which looks like a filigree tree root type of structure? Do I want a more chunky type of structure? We know that, and optimizers, topology optimizers, have gone through the pain of not being able to control that well, and now they're actually able to control that well. The limitation is if you do want a filigree, slender type structure, then you've got to have a very high fidelity mesh to do that. But again, yes, that's a very, very important control parameter. Sebastian says, are there some good sources for case studies, especially for application with thermal loads? I would recommend a good look at that GrabCAD challenge and GE. It's called the GrabCAD GE engine bracket topology challenge. If you Google that, then you're going to get a lot of hits on that. And if you go to the original reviews of all the results coming through, I think there were hundreds and hundreds and hundreds of candidate solutions. They fell into very different interesting categories. Some were definitely additive manufacturing, some were subtractive manufacturing, all sorts of different solutions, just showing there's many ways to skin a cat. What's an optimum? Well, there you are. There's 200 or more. And I think you could say there's probably 15 or 20 really good candidate designs in there, which were very, very different. So that would be one general case I would look at. And then for thermal loads, I think, yes, I should also say there's lots of extensions down into thermal loading as well. I'm afraid I'm just going to have to Google it. I can't think of any case studies. I think the two software that I used, if you go to their websites, you'll find that they've got examples in there. Erwin asks, what do you think of the quality of stress results from topology optimization? It depends how we view them and what stage of topology optimization. In the raw, our topology optimization we're fitting if we use, for example, the soft kill type of method, we've got a variation of density, we've got a variation of Young's modulus in our material at these boundaries, if you like, of the voids, at the edges of the holes. It's not real material, so our stress flow there is somewhat ambiguous. So this is why I call it like the one-eyed squint. Gives us some idea. If I were just to take the existing structure like a hard kill and say, show me the stresses through there, we'd have stress razors everywhere. So we're having to smooth the stresses. That's coming directly out of the optimizer. If we then backfit surfaces through there, so NURB surfaces, other forms of surfaces, and then basically essentially remesh in some way, maybe by fitting geometry and then remeshing that geometry, then we can improve the quality of the stress. Now we get a better stab at the stress. So it depends what level you're talking about. To get good quality stress constraints, for example, needs to be done well downstream. To get some idea of overall stress distribution, as I talked about my one-eyed squint, then I don't need to worry about it. As long as I understand it's an indication of the stress flow, not got hung up by particular stress razors, then I'm going to be okay there. Mike says the flying buttress pictures were compelling. Any books would you recommend that an engineer could enjoy to discuss the building design of cathedrals back then? It's a wonderful area, Mike. I only touch on it. I'm going to email a friend of mine, Jim Wood. I doubt if Jim Wood is listening. Jim has done a lot of research into natural structures. So he goes further and he talks about like biological structures and so on. There's a whole lovely analogy of how the flying buttress, the people there actually looked at analogies. The simplest is a brick, a building block brick analogy. If you turn the whole thing up and think about it, suspended chains, I believe there's a cathedral in Spain that somewhere has this analogy there. So yes, it's a great area. So Mike, I'll try and follow up on that. ANSYS can handle the validation on mesh and geometry level. Yep, there's all sorts of techniques across all of these different solvers. Again, I do stress I don't have any champions, or I'm not a champion of any particular approach. They're all changing. They're all doing a great job. What about multiple material designs? Olivia's asking. That's a very interesting one because now, like SIMP started off with basically like cell-like structure, multiple materials in there. Now we can actually go back to that. So there's now thought of, well, maybe we can actually have bands and blends of different materials in there, particularly for sort of additive manufacturing. So that's, again, another strong area where we can actually play to that. Sebastian says, splitting out regions around supports could help to exclude it from the design domain. Yes, we need to be very careful with that. Wherever we load or whether we support, we mustn't have that. We can get into absurd situations where you've got part of the structure which is loaded, and then you whittle that away. Now you've suddenly got something which is like just flying around in space. Same with supports. You can actually end up with mechanisms, rigid body modes. If you actually, you basically, it's the old story of, you've probably seen the cartoon, somebody sitting on a tree branch, wanting to saw the tree branch off. Unfortunately, they're sitting outboard of the saw, so they disappear when the branch disappears. That kind of thing can happen if we don't pay attention to controlling the supports. And again, it's a big topic, and what I would say there is we want to look at the supports not just simplistically, as I've done in perhaps in some of mine, but how the supports fit into the actual topology, into the optimization problem. What size should the supports be? Where should the supports be? That's another series of questions. We would just say, well, hold that boundary, load that boundary. But what does it mean? How do we actually get the load in? How do we get the load out? That's, I think, going back to Steve's point, that's the engineering coming into it. We can't just say, here's a boundary where we apply loads, take loads out, or take constraints out. We need to be, thinking about the, maybe a component level, but think how that component fits into the overall structure, even if we're not optimizing the overall structure. Sebastian makes a comment again, assemblies can be handled, different manufacturing constraints in the upcoming ANSYS version. I jump on all of the webinars which are coming up with any of the software vendors. This is what's new, this is what's coming up. I'd recommend anybody does that, because you guys are moving the goalposts all the time. It's not, new interesting things coming up there, so it'd be great. Erwin makes a comment, wouldn't it be great if the geometry boundary of the found solution and coarse topology optimization is used as a region for fine mesh and a slightly bigger volume box around it for new topology optimization? If you repeat this process, you get very fluent surface. That's a very good point, Erwin. If we end up, for example, like that last dinosaur type structure as it was described there, I ended up with very small volume fractions because I had a very big initial design space. If you can chase down design space by changing the design box size, then you keep that optimization search pretty tight. So there's all sorts of very interesting strategies like that, Owen. There's a whole sea of technology out there, and you touched on another very interesting area where we can do that. Rob says, hi Tony, a reference I can recommend to everyone in this interesting low-tech way to homogenize stresses is structures by method developed by Klaus Mathek, the Karlsruhe Institute for Technology, see Mathematics of Trees. That's actually where Marcel and I first came across this, and I must admit, I went over to Karlsruhe University, and we sat there and listened to we were over there for 3 or 4 days. I was a complete disbeliever, and I thought, what on earth is this on about? And then, after about a day, the light bulb went off. I thought, wow, this is really, really interesting. So, Karlsruhe University or Karlsruhe Institute for Technology, Klaus Mathek, that's a good reference. If anybody can see Rob's question there, then certainly that would be a good thing to look at. David asks, what do you consider the best approach for optimizing structures using either patterned or arbitrary lattices? That's, again, a whole interesting question. Patterned lattices means we talked about like gray areas of material. If you're using the SIMP method, we've either got steel or we've got chewing gum. Lattices are basically saying, well, this is our transition zone, this gray area, let's fill it with a lattice, which is effectively a compromised material, just the right material for the job. If they're patterned, then we're saying it's fixed patterning, and then the technology is a little bit easier, the programming is easier, and maybe the manufacturing is easier. Arbitrary lattices are more organic. They're going to flow and follow whatever. I would say probably to come up with like the optimum from a kind of a mathematical point of view, maybe from a philosophical point of view, maybe arbitrary lattices are going to give you the most efficient. But again, we've got to take that step back and say, from the point of view of manufacturing and controlling what we've got, is this what we want to use? So I couldn't really answer that question. I think you'd basically want to explore both those kind of approaches. I know patterned was the initial approach, because then we've got a template. We've got basically like a voxel patterning of the elements, which we can map into the solution. Now, if we've got arbitrary, then we've got to develop these filigree shapes, which again are kind of organic. So again, no right answer there. It depends on how you can make it, what your constraints are, what works practically for you. Sebastian makes a comment, there are overhang constraints taking additive manufacturing into account. This is correct. You can come up with something, for example, like a shallow roof. I deliberately avoid doing sketches this time because I get into such a nightmare with them. Imagine you're building something like a shallow overhang arch. Well, you're building up an arch. Additive manufacturing, you're building from the ground up. You build up the side supports of your arch, you get to the top of the arch. Now you've got that very, very thin shell of roof because you've only put the first layer in there. At that point, your additive manufacturing process collapses because it can't support itself, or you need to put supporting material underneath there. So there are overhang constraints to say we mustn't have an angle shallower than a certain angle, which gives us a more robust static solution to our structure as we build the overhanging, as we build the arch type structure. The direction cut we take to create that additive manufacture also dictates that. I view those at the moment really as kind of like band-aids. They're very, very useful, but eventually we're going to get to a stage where each step of the additive manufacturing process is going to have a little FE analysis behind it to say what can we do, what can't we do. So the way we actually evolve the component in the additive manufacturing process, it's a manufacturing process simulation, is happening simultaneously with our structural optimization. So there's early indications of that happening. Man, when that happens, maybe 10, 15 years down the road, we're going to get very robust, very, very efficient solutions coming out there. But at the moment, overhang constraints are kind of like I call it a band-aid, very, very useful band-aid to say, keep clear of this to avoid this kind of situation. So I got to really kind of cut it off there. There's a whole load of further comments in here, very, very thoughtful comments. I thank you for those. So we've run over considerably, David, but I think we'll wrap it up at this point. So I'll finish up now and hand over to David.
No problem at all. Thanks very much, Tony. And thanks to everyone for sending your questions in. I think that's been one of the big successes of this series, is that we've had so much interaction. I did have a look, Tony, to see if Jim Wood was online when you were talking about shape optimization. He's unfortunately not, but it was a little bit like Beetlejuice because he was typing emails to me while you were speaking.
Well, I never. Okay. Yes, the world is a strange place, isn't it?
Yeah. What I did do was he had an article on that topic in the October issue of Benchmark, and I'm just trying to. How's that?
Oh yeah, we got it now. Yeah.
Yep. So if you go to that web address, you'll be able to download one of Jim's articles for free on biological shape optimization that was featured in the October issue of Benchmark, I think it was. Just if anyone's interested in that.
Well, he loves that whole topic area. Yeah.
It does. It is a really interesting article to read as well. He writes very well. But yeah, so thank you very much, everyone, for your questions. A nice, lively discussion this week. Again, thank you very much, Tony, for putting your time aside and running this series with us. It's been great over the past few weeks. And we'll see everyone, hopefully, on the next session on June 12th on normal modes analysis and why it's an essential foundation to any dynamic response analysis. But for now, we hope you all stay safe, have a great weekend, and we'll hopefully talk to you all soon. Goodbye for now.
Bye, everybody. Thank you very much.